Superscalar processes. Depending on the method by which the flow of instructions can be carried out, processors can be classified as scalar, vector, or superscalar. In a scalar processor, a single item of data is processed for each of the clock cycles. Vector processors are similar to scalar processors, but they process an array of data for each clock cycle. The objective of superscalar processors is to obtain maximum speed. Hence, it is a combination of a vector and a scalar processor, as it includes a number of functional blocks and single item of data is processed in each of these functional blocks simultaneously. Superscalar processors follow instruction level parallelism, which is a technique that executes multiple instructions in parallel. The primary objective behind designing any processor is to enhance the overall processor performance. Parallel decoding is one of the basic tasks of a superscalar processor, and it affects the performance of a superscalar processor, and hence it becomes the interest of our study. This is the pipeline of a superscalar processor, where a number of instructions can be executed in a single clock cycle. Parallel decoding. As the rate at which instructions are issued increases in the case of a superscalar processor, when compared to the scalar processors, parallel decoding is a much more complicated process for superscalar processors. As the number of instructions per time increases, much more complex instructions require decoding, which causes the instruction decode cycle to prolong. To avoid a large decode cycle, partial decoding of instructions takes place when they are being loaded to the instruction cache. This process is known as pre-decoding, and the pre-decoder carries out a part of the decoding process while the instructions are loaded to the cache. Pre-decoding is opted as a solution to avoid long decode cycles. Instruction decode logic of a dual-issue superscalar processor based on Leon 2 processor. Leon 2 is a 32-bit processor, and due to its multiple on-chip features such as separate instruction and data caches, interrupt controller, hardware multiplier and divider, two 20-bit timers, 16-bit input-output ports, and etc. This processor finds its applications in a number of areas like digital dictation machine, fingerprint security system, GPS processor, and so on. As this processor finds its applications in a number of fields, attempts have been made to enhance the processor performance. We analyze the dual-issue Leon 2 model, which enables two instructions to go through the different stages of the pipeline simultaneously. The decode stage of this model deals with instruction dispatching and instruction dependencies, and the functions of this decode stage are to identify individual instructions, determine the inter-instruction dependencies once the instructions have been fetched, identify the branch instructions that change the control flow, support simultaneous access to register files, as the two instructions in the dual-issue pipeline would need to access operands simultaneously. The decode stage of a dual-issue pipeline deals with branch instructions, access operands, and inter-instruction dependencies. Branch instructions. In a single-issue pipeline, if the instruction decoded is a branch or a jump, the target address of the branch or jump is computed in parallel with reading the register files. The branch condition is computed after the register file is read, and if the branch is taken or if the instruction is a jump, the program counter predictor in the first stage is assigned the branch target rather than the incremented program counter that has been computed. In a dual-issue pipeline, instructions from which branches are caused come under the category of control transfer instructions, and these are classified into 4 kinds, which are call, branch, JMPL, and trap. On a call, unconditional branches are caused and the program counter changes with the instruction whenever it appears in the pipeline. A program counter relative delayed control transfer is caused from branch. This delay instruction will be annulled when A is equal to 1 and executed when the A bit is 0, and the remaining instructions in the branch cause conditional branches. In a dual issue pipeline, when a branch instruction enters pipeline 2, it does not affect pipeline 1, and the processor can continue to execute both the pipelines, but when a conditional branch occurs, it is first sent to the pipeline 1. When it goes through pipeline 1, the pipeline 2 instruction should stop executing and wait for the command from conditional code. If the branch is not taken, then the pipeline runs normally, and if it is taken, then the pipeline 2 stops execution as it needs to be updated. In an instruction fetch component of a dual issue processor, a comparator and a branch detector are added. Determining if the instruction coming into the pipeline 2 is a conditional instruction or not and checking for inter-instruction dependencies is done by the comparator. And detecting whether the branch is taken from the pipeline 1 or not is done by the branch detector. This decision in turn determines whether to execute or to cancel the instruction in pipeline 2. These are the comparator and branch detector blocks in the instruction fetch component. Inter-instruction dependencies. Once the 2 instructions are issued in the same group, the source registers read by the instruction in pipeline 2 cannot be the same as the destination register that the pipeline 1 will write into. When the instructions in pipeline 1 are load, JMPL, read or arithmetic logic shift instructions, and the instructions in pipeline 2 are one of the load store, arithmetic logic shift, or the control transfer instructions, then we need to check if the read of pipeline 1 is the same as the write of pipeline 2. The result from the comparator is sent to the multiplexer in the fetch stage and works as a control code. If there are no inter-instruction dependencies, then the program counter is incremented by 2 to get the next sequence program counter, and it is incremented by 1 if there are inter-instruction dependencies present. Access operands. Generally, in the scalar single-issue pipeline, operand 1 for the arithmetic logic unit is chosen from the register 1 and the 3 forwarding data, and operand 2 is chosen from register 2 and the respective 3 forwarding data of the single-issue pipeline. When it comes to the superscalar dual-issue pipeline, there are 3 additional options from which the operands can be chosen. These are the 3 forwarding data from the second pipeline, which is the pipeline 2. This is the implementation of the access operands in a dual issue pipeline where the runtimes and the performance enhancement rates are shown. Calculation of the cycles per instruction and the performance enhancement. The runtimes under different number of runs for single issue and dual issue processors are tabulated as following. The cycles per instruction is calculated as the runtime over the number of runs, and the performance enhancement rate can be calculated as cycles per instructions for a single issue processor minus cycles per instruction for a dual issue processor over the cycles per instruction of a single issue processor. From the calculations, the performance of a dual issue pipeline is enhanced by 30.1% compared to that of a single issue pipeline. Compared to the single issue processor, the performance of the dual issue processor is enhanced by 30.1 times as it uses twice the number of caches and multipliers that have been used by a single issue pipeline. Hence, the performance of a dual issue processor is greater than that of the single issue processor. The dual issue pipeline has a greater advantage if more number of instructions are dealt with. These are my references. Thank you.